Okay, so today I'm going to finish up just talking about the output of the regression that we get for the HCl Rovibrational spectrum, talking about the parameters that we have, um, comparing them to literature, and then also seeing uh, how to do the propagation of uncertainty, because we'll see that the uncertainty for 4 of the values is given to us right out of the ANOVA table. But then we've got to propagate the uncertainty for the last 2, the bond length and the force constant. Okay. So again, for the regression, yes. Oh, I thought you were raising his hand. Okay, so for the regression, we have, this is our y values and our x values. So the x input, this is the dependent variable here. Okay. So these are our columns. And we see that equation up there. Whatever column we build, the regression will give us the coefficient for that. Okay, so our columns, you're probably familiar with like the quadratic formula, a times x squared plus b times x plus c, right? The 3 coefficients. And so if you had a column of x and x squared and you ran that regression, the regression would give you a, b, and c. Okay, but your columns don't have to be pure x or pure x squared. They can be whatever we built up here. So when making our transition equation, we collected all of the alpha E terms. One of the alpha E term was times a negative m squared, and another alpha E term was multiplied by negative 2m. And so we had alpha E 2 places in our equation. And so we pulled those together, so we'd have 1 alpha E and everything it was multiplied by. Now we're going to make a column out of that stuff. So one of our columns is the minus 2m minus m squared. And then another column we collected on DE. We had all 3 of those things. We put them all together and made a column out of that. So that when we use that column as one of our x variables, it will give us a coefficient for that column. That would be x variable 2. This would be or 3. X variable 1, x variable 2, x variable 3. And that's what our ANOVA output will give us. Now, these columns are used to calculate in the model our y input. These are our experimental values. And so the ANOVA is looking to see how well these 3 columns can produce this y input, or the y values. Okay, so we go through here to the data analysis tool. And then if we don't have it, we go through the whole thing of adding it in through the Excel add-ins. And then we have it and we click it and we go to regression in that tool. Here's our Y range, our X range. If we were to select the labels, then we would click labels right here. And when we get that finished, we get this ANOVA output. And so I wanted to talk about these 3 columns down here. These are our structural parameters. Our intercept in our equation is here. This is our intercept. How do I know this is the intercept? Because there's no column associated with it. Okay? And then x variable 1, that's our first column that we made. X variable 2, so this is 1, this is 2, and this is 3. And this is the coefficients for those 3 columns. So if your columns were switched for whatever reason, then your x variables would be switched. Okay, but it's in the order of the columns. Now these are the coefficients. So this is nu 0, this is BE, this is alpha E, this is DE right here, and these are the standard deviations for these. Now do y'all remember the difference between a population and a sample? Have y'all heard that language in terms of statistics before? Yeah, exactly. So how many observations do we have in this? 24. Okay, so we're dealing with population statistics. So these are sigmas, not S. There's another way to think of it too. So so these are population standard deviations. And then here's our statistical significance, the p-value. Okay. And so this is really quite good. This is it's 99.999 dot dot dot, times 35 nines. It's 1 minus that. So 1 minus P equals confidence. And so this, I probably have that up here. So our null hypothesis, this is just a little bit of background on the statistics. You really shouldn't be quoting p-values in anything unless you know what the null hypothesis is, because the p-value is the probability that the null hypothesis is true. So the null hypothesis is that the coefficients are all zero. That's another way to state it, okay? That there really is no statistically significant nu zero or BE or alpha E. That fluctuations in the data gave us that value. So what's the probability that fluctuations in the data, just the scatter in our peak picking, gave us this coefficient of 2,885? This is the probability. It's 8 parts in 105. So 10 to the 105th power. Okay. And so this is that probability that the null hypothesis is true. So this is not generated by random noise. That is generated by statistical significance in our data. It's matching the scatter in the data. Okay, if p-value is greater than 0.5, we throw that column out and redo the model. And this typically happens for the intercept. So let's say, let's say you have a model here, and your data is like this, and it comes down, and your intercept is 2,885, just like ours. And your p-value is equal to 0.07. So that's saying there's a 7% chance that that huge number is really zero. We would throw it out and set it to zero, like we would make it go through zero. Now, how could a number that big be not statistically significant? Well, it a lot of times depends upon how tall this y-axis is. If this value has a measurement of, say, 200,000, on the scale of 0 to 200,000, 2,000 is not very much. And so a lot of times we see insignificant intercepts when we have huge y values. Like in chromatography, we're doing area under the curve. We get peak areas of 200,000, 500,000, and our intercept may be 12,000. But the statistics on that intercept, the p-value is too high. And so we throw it out and we set the intercept to zero. We anchor it to zero, and then we just model the slope of the other things. So that's just when we go back up here to our selections, if our p-value was too big for the intercept, and we want to throw it out, then we would select this right here. We would say our constant is 0. And then it would not model the intercept. It would fix the intercept at 0, and then it would just model the other lines. Okay. Now, whenever you do trend lines in your research, you need to do a regression, because you want to get these standard errors right here. And Tommy, in his graphs, he showed his calibration line, and he showed the uncertainty in those calibration lines. Okay. So anyway, that's why you want to do a regression analysis on your calibration lines. Okay, so I've calculated B now. This is a new slide. Well, it will be. So how do I get the bond length for a diatomic molecule? So we want to get our bond length in angstroms, and we want to use the reduced mass, say in grams per mole, off the isotopic values, that we can find online easily enough. And all of this other stuff doesn't change. These are all your conversion factors, pi, speed of light, and things like that. And so we just consolidate all of that mess into one huge constant, but we keep all of these significant figures because we don't want to introduce any kind of bias into our analysis. So we definitely want to use, look how many figures I have on, significant figures I have on Avogadro's number. Here's Planck's constant. It's not just 6.022. We got to keep all of these others. This is Avogadro's number. This is Planck's constant. This is the speed of light. I keep all of them. That way I'm not introducing any bias. If I round any of those, then I'm introducing bias. Okay? Not much, but the precision of our analysis is such that we don't want to screw it up by using 6.022 for our Avogadro's number. And look at the significant figures we have here. 2.885 down here, and this is going to tell me where my first uncertain digit is. And my first uncertain digit is in the thousandths place. So this is how many sig figs I have in my vibrational frequency. So if I use 6.022 in Avogadro's number, I'm screwing up the 5th decimal place. And here I've got 2 more decimal places to go. I've got 7 sig figs here. So I don't want to round my constants. So we keep those constant values as far out as we can. And so this is our rotational constant. So we can rearrange this to get the bond length. Okay. Here's our frequency of vibration, and we want to get the force constant. So rearranging that, we can solve for the force constant. Okay, and notice the units in our force constant, the wave numbers cancel with the centimeters here, the speed of light in centimeters, and so then this is a second squared. I've got a kilogram and I've got a second squared. And so how does this kilogram per second square equal newton meters for newtons per meter for the force constant? Well, I can multiply by a meter over a meter. And this piece right here, a newton is a kilogram meter per second squared. So this piece right here becomes the newton, and it's a newton per meter. Okay, so those are the equivalent values. Now let's take a side trip and talk about the uncertainty in this value, because we have uncertainty here in our frequency. We have no uncertainty here, so these are all infinite sig figs. But what about our frequency? It's got uncertainty. Our reduced mass, it's not infinite, but we know those mass values, to 7 or 8 decimal places. So we know our masses really well. It's this one, this vibrational frequency, that's going to be the largest source of uncertainty in our force constant. So let's do a side trip on propagation of uncertainty. There's a full lecture on this propagation of uncertainty on the YouTube playlist, so you can watch that whole thing. I'm just giving you a short piece of it right here. So if I have addition and subtraction, so these are 3 numbers. I'm adding 2 of them, subtracting a third, and calculating y. So that's the math I'm doing, addition and subtraction. This is the uncertainty operation. So this is the uncertainty in y, and it's just the sum of the squares of the uncertainties of each of those pieces with the square root. Okay, these are called variances. So the variance in my result right here, you see if I squared both sides, I get rid of the square root, and the square root will be over here. This variance of the result is equal to the sum of the variances of each individual piece if I'm just adding and subtracting. What's the most common operation we do in the lab where this equation applies? What? What is the most common operation in the lab that we do where this top sum, uncertainty analysis applies? 4 things together. So we're adding. So we're measuring with a grad cylinder, a burette, or a mass balance, because we have 2 measurements, before and after, and we're subtracting, right? Top volume minus initial volume. So adding and subtracting. So in subtracting, we have uncertainty with our first measurement, uncertainty with our second measurement, and so this is how you combine those uncertainties. Okay. So if you have a 0.05 on a burette, 0.05 standard deviation, that's your uncertainty, and you have 0.05 in the second one, after you square those, add them together, take the square root, it becomes 0.07 because you're a little uncertain on both ends. And so the combined uncertainty is 0.07. So you would need to report that as your uncertainty. 0.07, not 0.05. 0.05 is just for one measurement. Even a balance, when we measure, we're actually tearing out the thing. Well, that's a measurement. We're making it 0, but it's 0 plus or minus 0.0002. And then we weigh it, and then what we weigh is also 0.0002. So we have the combined uncertainties. So now let's do the products. So if I'm doing a calculation where I have two numbers multiplied by each other or divided by a third, this is our uncertainty equation. So this is the uncertainty in our result. It's the result times the square root of all of these things added together. It kind of looks similar to this, only instead of straight uncertainties, these are RSDs, relative standard deviations. So this is the standard deviation relative to the value of the number. And so this is the RSDs squared for the result, okay, is equal to the sum of the RSDs of each individual piece. That's for multiplication, okay. When do we have this? Well, in our examples for the bond length and the rotational constant and all of that, we're going to have these multiplication ones, okay. Or we might even have this one, exponentiation. So if we have something squared, like a squared, well, x equals 2. Okay, what if we have the square root of a? That's a to the 1/2 power. So x equals 1/2. So this one is just RSD of the result is equal to x times the RSD of the thing that you're taking the square root of, or the square. So let's apply this to our situation. So I've done the work for you. Okay, so here's our calculation. So this is our three equations here, and this is the one that applies, because see, we have our value that has uncertainty and it's squared. So x is equal to 2. So our relative standard deviation of k is equal to 2 times the relative standard deviation of nu 0. So here's the equation. So the RSD for k here is sk over k. And the RSD for nu is S nu over nu. I could use sigmas as well, but I'm just using S here. And so all I've done here is I've just taken this k from the denominator and moved it over to the right. And so I know all of these numbers. I get that from the regression table. I get that from the regression table. I get that from the regression table. And I know where 2 is on the keyboard. Okay. And so that's how we calculate the uncertainty in our force constant. Okay. Let's do the bond length now. So here's the previous slide. And this is, again, the one that applies. This right here is the square root. So the RSD in our bond length is 1/2 of the RSD of the rotational constant. And so, RSD is, SR over R, and the RSDBE is SBE over BE. And so I've moved this R, over to the other side of the equal sign. And that's the uncertainty in our bundling. So that's the propagation of uncertainty that I'm talking about in the report. Okay, so I've done it for you. It's right there on this slide. Okay. Now let's look at it in Excel. Okay, so these are the results. So we have our from the ANOVA table, we've got our coefficient, nu 0, and these right here are our S, values, or SY values, if these are Ys. So from our little regression analysis, our little uncertainty page, they have Y and you have SY. Okay. Now we want to capture a 95% confidence interval. So for populations, we can use Z 95. Yeah, for population statistics. And so if this is the Gaussian distribution of our random errors in our result, okay, our normal distribution, plus or minus 1.96 will capture 95% of the area under that curve. So just random noise will move our vibrational bond, our vibration one way or the other, or our force constant and so on. And so we're just going to take these values here and multiply this by 1.96. And that's this. See, it's roughly 2. It's 0.44. It's close to 0.88, okay? It's not exactly 2, though, but it's close. So all of these 95% confidence values are about twice the standard error. And then what about the RE and the KE, or the K? That's just using that propagation of uncertainty on the previous page. So we took the standard errors for nu, and we calculated the standard error for K. We took the standard error for B, and we calculated the standard error for the bond length. And then we multiplied that standard error by 1.96, and this is our bond length. Look at this. Where does our uncertainty begin on this bond length? Out here. That's crazy. Look how well we know. Like, we've measured the bond length of HCl to, point 0.0000, plus or minus 5 in that fifth decimal place of angstroms. That's crazy. An angstrom's 10 to the minus 10 meters, and we're even 4 more divisions smaller than that, powers of 10 smaller than that. So that's pretty impressive. We're at our uncertainty is 53 micro angstroms. That's crazy. I don't know. I'm excited about that. And why is it? It's because we have so many peaks. We picked all those peaks. So then how did we do? So let's compare it to literature. Now, I did, used to, I would go to the NIST webbook, and this is what you guys can do. You go there and you type in the molecule HCl, HBr, whatever. Maybe you put the isotopes in there too, HCl35, HCl37. And there'll be like constants of diatomics that you can click. And it'll give you the table, and it'll have the vibrational frequency and the bond, the rotational constant and all that. You can pull all of those things out. So yesterday, playing around with this, I thought, well, I wonder how good Grok is. I don't really like any of the other AIs. The Grok, it does better, I think, of pulling data off of the internet. It's just, I think it's superior. So I went and asked Grok to pull the literature values and from good sources for carbon monoxide, for both isotopes of HCl, both isotopes of HBr, HI. Yeah, I think those were the 5. It went out and found them. It dug through the NIST webbook. It pulled them out for me and put them in a table. It's unbelievable how good it was. And so it's, I would have you consider using that to collect those, and then check on them, like follow the links. And okay, it sounds like you're still doing the same thing. Like you follow the link and you find it on the webbook and all that, but you're not having to pull it all, and copy and paste it. The tedious part's done. You can just check their sources to make sure Grok is not lying to you and creating a hallucination and saying that it's checked, this website. So you follow up and check the AI, but your task of copying and pasting and putting it all in a nice document is done for you, and it's really nice. Okay, so I would encourage you to check that out. So here's our regression data here. Here's our derived constants here. Here's our 95% confidence intervals. Okay. Here's our coefficient of variation. So that's this divided by that times 100%. So like our a measure of our uncertainty in terms of percent. Really, really are good. Our worst one is the centrifugal distortion constant that we have here, 5168. plus or minus 46 on that scale. Okay, so that's the worst one at 0.9%. So we're still really, really good on that one. And then here's the literature values from NIST. I should say NIST, not the CRC. I went and got these recently. And so here they come in at really close, okay? Here's our absolute bias. We're off by 0.57 wave numbers here. Look how close we are on the rotational constant and on the alpha E, the rotation vibration coupling, and the centrifugal distortion. Look at that. And then also the bond length, and then the force constant here. So here's our bias. This is the absolute amount that we're off in terms of wave numbers here, angstroms here, and newtons per meter here. And so here's our percent. So if we take this bias and divide by the literature value, that's the percent that we're off. So we're only off 0.02%. Our worst one is here. We're low. The negative sign means we're low. This number is less than this number. Okay. We're low by 0.28%. Oh no, 2.8%. So that's the worst one. And this is, if we take 1 minus this, that's our accuracy. So we were 99.98% accurate on the vibrational frequency, 99.96% accurate on the rotational constant, all of these. And your numbers should look very much like this. Okay. Yes.
So on your J value,
Yes. I said 9 per centimeter. Yeah, so newtons per meter would be fine. Yeah. So I'm not going to go in there and it should be this number. Yeah, that's what I was aiming for. Now, the one thing that gives me a little bit of heartburn is I've taken my uncertainty values, I've multiplied them by 1.96 so I could get the 95% confidence interval. So I'm 95% confident that the true value should be within these limits, and none of them are. That's weird. So that gives me a little bit of heartburn. I actually don't know why that's not the case. So I'm not biased by much. Here's my percent bias. I mean, I've got really small biases. So my precision is as perfect as I can imagine. So here's our target, right? Here's the bullseye. And our data is right here. You see that? 27 measurements, computing these values. I've got a really tight cluster. That means these are really small numbers. Okay? This is my uncertainty divided by the value. All of these are really, really small. So my precision is great, but I'm off. Not much. These are the percentages that I'm off. This distance for the worst one here is only 2%. I'm only 2% off, but I'm off. And I know I'm off because my precision is so small. It's so good. I don't know why. Is it because my spectrometer is not calibrated? Maybe maybe the spectrometer is off by 2%, so my frequencies are shifted or something like that. I don't know. Okay, but this is, I'm very happy with the precision, but I'm bothered by the accuracy. So. Any ideas? I'm not trying to teach you because I don't know. Now, how did we do the peak picking? We picked the maximum, right? So let's try something new, and this is getting into the extended project, okay? One of the things that we did in our peak picking was pick the maximum value, okay? Maybe that's not accurate enough. So how can we get more accurate peak centers? We can go to deconvolution. So let me swap my projector and everything around. Sure. Okay. Okay. Come on. Yeah. Okay, good. Yeah, no, it's trippy. This is what I want right here. Okay. So this is the deconvolution tool that I've uploaded to Blackboard. Okay. Now, what I've done here, there's a whole procedure here. So I know that, I mean, I can read your faces. Some of you are really nervous about this extended thing. But I've got very clear instructions on what to do. So this is a tool. Instead of having you build this spreadsheet, I just provided it for you, and I'm teaching you how to use it because it uses the process of deconvolution. When you read the handout, you'll see, okay, we've already done convolution. When we did our stick spectrum for the particle in a box, and then we put a Gaussian on every one of those sticks, that's called convolution. We're taking the stick and we're convolving it with a Gaussian line shape. And then the next stick has a Gaussian, and the next stick has a Gaussian. If we model our spectrum with a Gaussian, how do we get that Gaussian? We have to provide a peak center, a peak height, and a peak width. Well, the peak center and the peak height are the sticks. So if we model the whole peak with a Gaussian, we get the stick. And we get a better idea of what the peak center is. So notice here, I've got in this chart, I've got these 4 peak centers. So if I'm going to take this, let's do the bigger one, 29, 25. I'm going to make it 29, just 29, 25. Look how it moved. You see up here, there's a big difference between this peak and that peak. Okay, let me do 25, 29. It needs to go up. I've got this plot going to the right. This is the big wave number side. This because that's later on when we paste this into a table. I wanted them all to be in increasing order. Okay, so let's go to 25, 26. Oh, too far. What happened? 26. Undo. Okay. 25, 26.
It's going to be on direct axis.
Oh, 29, 26. Sorry, 29, 26. I knew something was wrong. Yeah, so it's a little too high. How can I measure how good the fit is? Well, I've got all of these columns down here. I've got the experimental spectrum. I've got this comparison spectrum and a high resolution simulation. And I'm taking the differences between the experiment and this comparison spectrum to calculate a standard deviation of the fit. And so if the peaks don't line up, I have a high standard deviation, the square root of those residuals. If I match it perfectly, that standard deviation would be a minimum value. Okay. So let's look at this number right here, 0.4. I'm going to do undo. It's 0.1, okay? Oh, undo again. Undo. So there, back at the original, it's 0.03, okay? So now let me do 25, 27. 29, 27. So see, that peak doesn't line up at all, okay? And my standard deviation is 0.12. It's really high compared to the 0.03. So I can move these all around. 29, 22. Okay, so that's really bad. You see? And so what you want to do is I've given every person in the class 4 peaks. Like 1 or 2 people have 8 peaks to do this twice because I needed to get through all of the numbers and so on. And so so you zoom in the x-axis of this plot. This is right here. Zoom the plot into the range of your 4 spectral lines. And so you've already assigned the HCl spectrum. If I say you've got R5 and 6, then you go zoom in on R5 and 6, okay, and get those 4 peaks, the 35 and 37 for R5 and 6 on this plot. And then you set the plot parameters here to the same limits, 2920 to 2950. You set the comparison range to 2920 and 2950. Okay, so you have those match what's in the plot. And then don't worry about the baseline. Then you start moving your peak centers and peak heights to where it matches. And when you get close, let's see, I know that I need to go up on this one, so I need to go 29, 23. And then this one I need to get to, that's too high, 29, 26. Okay, that's pretty good. Let's say this one I did 29, 42. Okay, so that's pretty close. And this was 29, 45. Looks right, it's right on that thing, 29, 45. Okay, so I've gotten it kind of close by hand. Okay, and I can look at this to see if it's better or worse. Okay, but I can just visually look at it and see that this peak needs to go up a little bit. And so I'm going to take peak number 1 and go 29, 23.5. And it moved up and it got better. Okay, now what I want to do is I want to go start using Solver. So Solver is under that data tab right here. We did the add-in. I'm going to click that, and I'm going to set this target value. This is our set objective value here. That's this one right here, to a minimum. It's never going to reach 0. We certainly don't want it to be a max. That would make the fit as bad as it could be, right? So we want to set our standard deviation of our plot to a minimum, and we're going to let it change certain cells. I'm going to start out by changing the baseline. Like if your chart is not exactly at 0 for the baseline, then this fit doesn't work as well. And so I can let Solver change these two variables to make our standard deviation a minimum. So I hit solve, it moves it around, and then it pops up and it says, Solver has converged on the current solution. All constraints are satisfied, and you hit OK. So it changed these values to make our baseline better. You can kind of see it's not exactly on the baseline. Okay, we'll fix that later. We'll go through it a couple of times. All right. It's not fixing our baseline because we have these peaks that aren't exactly in the right spot. So next we use the Solver to minimize the standard deviation while changing the peak centers. So we hit Solver again. Same objective, but we're going to pick this value and we're going to pick our peak centers. So B23 through 26. And we're going to hit solve. Now it's moving the peak centers around while it minimizes the standard deviation. And it's way faster than you. It's changing these, 1,000 times a second. Notice how our peak centers are in good shape now. Okay. And then we do Solver again and we change the peak heights. So we want to give it the peak heights. So we do Solver again, change the peak heights. Let's see if it, oops, I went too far. Just get these 4 cells. Okay, hit solve. Okay, so now the peak heights are changed. Now what we're doing is we're using all of the data points in our peak to find the center, the width, and the height. Do you see how that's better than just the highest data point? Because the data points individually can be affected by noise. And so we've got 2 data points up here at the top. Which one is higher than the other may be just a function of the noise in the data. And so a single data point, the peak maximum, could be affected by noise more strongly than the whole peak, all the data points in the peak. So deconvolution is way better in that it uses all of the data points across a peak to find the width of the peak, the height of the peak, and the center of the peak. And so we're just using Solver to minimize the error between our model and our experimental spectrum. Our model is the convolved spectrum. So, and then we could change the line width. I'm just going to now give Solver more freedom. I'm going to let Solver change all of these, so the centers and the heights. I didn't want to do this at the beginning because sometimes Solver runs away and like it'll produce a really fat peak or whatever. That happens if the baseline isn't fitted. It'll take a peak and make it into a baseline, and that'll screw things up. So and now it changes peaks, heights, and centers. And I'm going to come back and redo the baseline because the baseline is not so great. So I'm going to do solver again, and I'm going to do the baseline. It got worse. That stinks. Huh. Interesting. Yeah, that's really interesting. I don't know why that is. But it looks really good in terms, I mean, this was actually lower than we started with. We had 0.03 when we started, and now it's 0.029. And so I'm going to go with that because this baseline is not shifting our peaks. And notice now what we have. If I were to zoom in, let's see if I can zoom in. Really zooming in. Okay, right here is the center of the peak where my mouse is. You see it? But if I were picking the peak maximum, I would be off. I'm not at the center of the peak if I pick the peak maximum. So the convolution gives me the peak center. So it's not off much. But remember our bias? Our bias was off just a little bit. And this might be the source of the bias. Okay, so I wanted to teach y'all how to do spectral deconvolution. So that's the extension of this project. So you did the project this week. Next week's extension is the deconvolution piece. Okay, just for HCl. Look at this one. This one is pretty far off. This is the peak maximum that you picked, but the center of that peak is right here. And here, this peak maximum is low. This one is high. That one's low. This one's high. So it looks like in our case, the low and the high kind of canceled out, but what if it didn't? What if all of our little peak maxima were all on the high side? Then our analysis would be shifted and our vibrational frequency would be shifted ever so slightly. And that's why we want to use peak deconvolution. Now, I wanted to, this looks confusing perhaps to you, but it's really not that much work because each person is going to do only 4 peaks. So what I just did in like 15 minutes, that's all you have to do for the deconvolution, is you have to fit these 4 peaks. And then you're going to go put those into a shared Excel file. So like whatever your peaks, it was like R6 and 7 or something like that. You're going to take your 4 frequencies and intensities, this right here, you're going to select this information right here for those 4 peaks, and you're going to go paste them in that table, okay, where your name is. And then you're going to do your 4 peaks, and you're going to do your 4 peaks, and so on. So you're going to build this table. So we'd like to have that done by the end of Monday. So on Monday, work on the deconvolution. You got all of this stuff for this week due Sunday night, so don't worry about it yet, okay? But on Monday, do your deconvolution, get your 4 peaks, and get it into that shared table, so that everybody can use that table then to do the analysis, the reanalysis of HCl 35 and 37. Okay? That's the reanalysis of HCl 35 and 37 using deconvolution. And then I also wanted you to extend your analysis skills to some other molecule or some other transition. So there I've got carbon monoxide, HCl 35 and 37, but one of them is an overtone, and it's on a higher resolution experiment, spectrometer. And then I've got HI, and on HI I have the fundamental, and I have the first overtone and the second overtone. So like I may have given you the second overtone and given you the third overtone, or the first overtone. And so you're doing the same analysis, but with for a different molecule, a different set of literature values and so on. Someone got HF too. So we have HF, HI, HBr. BR, that's different because you have a 79 and an 81 isotope. And so you have to do the isotopes for HBr. So everybody has a different assignment for next week in terms of the other molecule or transition. And that's all outlined in the handout that was posted last night. So I'll stop the video here, or just stop talking and ask if you have any questions about the current project that's going on right now. Let's do Sunday night. Yes.
Yeah, for the Gaussian part of it.
I'm going to just cut the Gaussian part. I cut it out of next week's thing. I'm just going to cut it out of this one. I haven't given you guidance in terms of what basis set to use and so on. And so I'm thinking that's just going to be a distraction. Okay, it's so let's just focus on the row vibrational stuff. If you wanted to do the Gaussian, or if you've already done the Gaussian, that's great. But let's just focus on the spectral comparison to literature.
So anything here
Yeah,
that
if it says
Gaussian,
Gaussian, yeah, just cut it. Yeah, let's just cut it. Yeah, I don't even have those calculations done right now. I mean, I have HCl, but I don't have any of the others. And so I went ahead and on the extended project, I went ahead and cut the Gaussian out of it just to focus on the deconvolution and then the new transitions. Yeah, question?
Generator one.
Okay. All right. All right. Yes.
Yeah, okay, and so then for assignment table,
Yes.
I know what that is in the Excel,
Yeah.
but when you have it as table one for the project,
Mhm.
how much of that table just the frequency and the absorbances, is that?
No,
what
let's do
consists-
frequency absorbances, the branch, RP, and the J double primes.
Okay, so
So
the
that's
four.
it, just to the J double primes. Yeah. Yeah. Because the other, the M and all that stuff, that's really just for the regression. So you really, once you've assigned the J values, then you could generate all the others. Like if this was a report that you're putting in the literature, that's the minimum that I would need. I would need the R branch and I would need the J values. Yes. Yeah. Yes. No, it's just whether I sorted the table in increasing values or decreasing values. So if I sorted it in decreasing values, then the high value is at the top, and that'd be the R12 or whatever. And if I did increasing, it'd be like the P11. So that's the only difference.
For the 95% confidence interval
Yes.
that you want in
Mhm.
table two, do you want them formatted like that's what you have right?
Yeah, yeah, it'd be great. You could also write them like this, okay? So I also kind of like this, where I could have put 8.6 right there. So do you see where it is? It's in the third and fourth decimal place. See where the 8.6 is? The third and fourth decimal place. So the parentheses here indicate that I'm uncertain. Since I have two values in parentheses, that tells me I'm uncertain about the two previous values. Does everybody see how you're writing the uncertainty? You can do either one because they're both acceptable in the literature. Okay.
So what you're talking about is those two values that you have in the parentheses.
Yes. Yeah. And so if I were to do that with this one, I could put parentheses 8, 9 like that. And so it's telling me that I'm uncertain in these two values since I have two values. If I didn't want to use two values, if I just wanted to use one value, like I would get rid of this 7. I would round that up to 1, and I put a parenthesis with a 1 there. Because see, it's the fourth. See over here, this is the fourth decimal place. And so I round to the fourth decimal place, and I put that parenthesis next to it. So I'm saying I'm uncertain with plus or minus 1 in the fourth decimal place. And both are acceptable. 1 unit of uncertainty or 2 units of uncertainty, but 3 is not. It's not really acceptable. I mean, if you're uncertain about 1 unit, you're really uncertain about the second unit over, the second place value, and the third place value is ridiculous. Okay, but they keep 2 values of uncertainty many times as a guard digit to prevent rounding errors and so on. So, like this, if I were to take my uncertainty and use just 1 unit of uncertainty, I'm actually rounding up to 9, and it indicates that it should be less than 9. Not much less than 9, but less than 9 in that place value. So that's why we keep 2 units of uncertainty or 2 places of uncertainty is what I'm trying to say.
Oh, so what you're saying is when we show our experimental values, we can, for those 95% confidence intervals, put those last numbers in.
Yes. 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 Yeah. Very good. Glad we got that. Yeah. So it's not seeing it, and you can just put in the text, or if it's in a table, describe that the numbers in parentheses are 95% confidence values, because you got to tell people what you're reporting. Is it a standard deviation, or is it 1.96 times the standard deviation? Yes. Correct. Correct.
And then
Yes.
put a note like at the bottom of the
Yeah,
table,
just
like,
tell
this
people what
format.
what you're putting in there. Yes. Yeah. It's about communication. Yes. That's really what I was doing here um, in lecture. Okay. But if you wanted to, in your discussion, that would be a neat thing to show if you were like discussing the precision is really good, but the accuracy is off, then to produce a table like that. Those tables and figures that I asked for are the minimum. If you wanted to include something to make a point in your discussion, that's great. Now this is not a journal article. You do not have to discuss things, you know, forever, but you do need to convince me that you know a little bit about the topic. Okay, so those are the polls. Being completely concise, where I don't even know if you know what you're talking about, or like trying to write a book. We don't want a book, but I need enough for you to convince me you know what you're talking about. So we need to move more towards enough writing for you to demonstrate your knowledge, but not so much that you're trying to fill pages or anything. I do not care. I do not want you trying to fill pages. I want you just discussing the question. And if you want to tell me something about the bias and the accuracy, then do that. But don't feel like, oh, I got to talk about bias and accuracy, and you write a bunch of stuff that doesn't make sense, because then I'm going to take off. You see what I mean? So only include stuff you're confident about and write it up. Yeah. Yeah. Because that's life. I mean, if I'm going to write a journal article, I'm not trying to fill pages, and I'm not trying to just write stuff. Just, go ahead. No. I like to use the word bias because error sounds like you made a mistake. And so when you're talking about error analysis, I know that's a common way to say it, but I don't like the phrase, to be honest, because they are the same thing. Percent error and percent bias. If you're talking about accuracy, and that's the other thing too, bias has to be accuracy. Whereas percent error could be precision or accuracy. Like I could be random error or systematic error. So if I don't have random or systematic, then I don't know what error means. But bias is systematic error. Yeah. No, the random error comes from these values. These are my random errors because they're plus or minus. Bias is the directional thing. It's either high or low. This is biased high. This is biased low. But the signs mean something, and it's always experimental minus literature, because if experimental is low, we want it to be negative, and if experimental is high, we want it to be positive. So the plus and minus signs carry information. Okay.